So the topic now is absolute convergence. And then our last tests, basically the ratio test and also the root test. The ratio test is the more typical one you're going to use. So first you have to have the notion of absolute convergence. The absolute's like an absolute value. So if we have a series, we say that it's absolutely convergent if this converges. So basically you just take every term of the series and hit it with absolute values. So all the terms are positive, and if that converges. So if you start out with a series where all the terms are positive, then this doesn't affect anything. But if you start out a series where some are positive and some are negative, then it might be alternating. If it's strictly alternating, then you can think about the alternating series, but it might not be strictly alternating. And nevertheless, this is a good way to test it. So you just get rid of all the minus signs, and then you ask, does this series converge? Because here all the terms are positive, so we have a bunch of tests for series with positive terms, right? That's the integral test, the comparison test, and then a test we're going to do in a few minutes. And this is useful because of the following theorem. If you have a series and it's absolutely convergent, then it's convergent. So if you take a series and you hit the terms with absolute value and this guy converges, then the original series converges. That's what this theorem says. So for example, suppose you had a series like this. Now the sign of n is sometimes positive and sometimes negative, but there's no simple pattern for when it's positive, when it's negative. So rather than worry about it, we'll just hit it with absolute value signs and look at the series where these are the terms. But now, since the sign is always less than or equal to 1, I can compare it to this series. But this is, of course, a p series with p equals 2, so we know that this series converges. So by the comparison test, this series converges, right? Because all the terms are positive. So that says the original series is absolutely convergent, hence convergent. Now here's another example, the alternating harmonic series that we've looked at before. If you test it for absolute convergence, then you just get this. But we know that diverges because that's the harmonic series. So here's a situation where this guy converges using an alternating series test. We already discussed that. This converges, but this does not. So this does not converge absolutely. What we say in a situation like this is that it converges conditionally. So it converges, but it doesn't converge absolutely. All right, so there's really two ways that a series can converge. Conditionally, which is nice, or absolutely, which is better. Why is it better? Well, we'll get to that later. So this is a good way to test if a series converges. See if it converges absolutely. Again, because then all the terms are positive, so we have a number of tests that we can use for that. And now we're going to go to basically the last major test we have for convergence, namely the ratio test. The ratio test is sort of modeled after what goes on in the geometric series. See, in the geometric series, that's like down here. The geometric series is this, a times r to the n. That's the nth term. When you look at the ratio of successive terms, the n plus first term divided by the nth term, the ratio is r. Because with the geometric series, you get from one term to the next by multiplying by r. That's these powers of r. So these ratios are always the same r. And we know from a while back that if r is less than 1, positive and less than 1, then we get convergence. So the ratio test kind of mimics this. Now I just have any old series, so it's not going to be a geometric series. But we do the same thing. We take the ratio of successive terms, the n plus first term divided by the nth term, and then take absolute values. And now the deal is pass to the limb as n goes to infinity, and let's assume it approaches a limit, L. That limit could be less than 1, could be greater than 1, or of course that includes infinity, or it could be 1. I suppose you could also have the situation where there's no limit, but typically you're going to get these situations. So in these three different cases have 3 different answers. So in the first case, when this approaches a limit that's less than 1, then the series converges absolutely. On the other hand, if it converges to a number bigger than 1, it will diverge. What about if it converges to 1? Well, then you don't really get an answer. No conclusion. Some examples would converge, other examples would diverge. So if you get this, then you have to do something else. This test hasn't really given you any conclusion. And the idea of the proof, I'm not going to go through all the details of the proof, but the idea is to compare it to a geometric series, right? Geometric series, these successive ratios are always the same. And here they're not, but if they approach a limit that's less than 1, and that's kind of like the situation where r is less than 1, you can actually compare the terms to a geometric series that converges. And yet that you can use that to show convergence. But if it converges to a limit that's bigger than 1, that says basically, at least in the limit, for large values, this term, it will be larger than this term. Right? The n plus first term will be larger than the nth term if this limit is bigger than 1. So, and then the term, so that means successive terms are getting larger. Well, you can never have convergence in that situation, because in order to have convergence, the terms have to go to 0. So if they're getting larger and larger, they're not going to be going to 0. So that's why you get divergence here. And in the third case, it's just a matter of pointing out some examples, like a p-series, summation 1 over n to the p. If you apply the ratio test to this guy, you'll find out that the limit's 1 for all values p. But of course, we know from before, some p-series converge here, and some diverge in this situation. So there's examples where the limit goes to 1, some of them converge, some of them diverge. So in general, you can't reach any fixed conclusion. You have to go use some other test to get yourself an answer. So let me show you a couple examples of how you use the ratio test. One of the prime situations in which you're going to want to use ratio test is when factorials are involved. So let me remind you about the factorial. It's very simple, right? If n is a positive integer, n factorial is the product of all the integers less than or equal to it. Right? So for instance, 5 factorial would be 5 times 4 times 3 times 2 times 1, and so on. You're going to find that series that involve n factorial are generally handled by the ratio test, because the algebras just can be handled. Here's the basic idea. If you take n plus 1 factorial and divide by n factorial, almost everything cancels, because you think of n plus 1 factorial is n plus 1 times n minus 1 times n minus 2, and so on. In other words, you peel off the first term, n plus 1, and what's left is n factorial. So that cancels the n factorial on the bottom, and just get this simple thing. So factorials like this, almost all the terms cancel. For example, look at this series, summation from 0 to infinity, 2 to the n over n factorial. Let me also just remind you that really, just by definition, 0 factorial is defined to be 1. So it makes sense to start at 0. So this is like 1 plus 2 squared over 2 factorial, 2 cubed over 3 factorial, 2 to the 4th over 4 factorial, and so on. So let's apply the ratio test. The n plus first term is this guy with n replaced by n plus 1. So that's this term up here. And then I divide by the nth term, which is this. Now do the algebra. So I write this. This is a fraction of fractions. So I put this one here, and then I multiply it by the reciprocal of this there. Now the n plus 1 factorial and the n factorial, as I said here, cancel except leaving an n plus 1 downstairs. And these powers of 2 all completely cancel except leaving one more power upstairs. So this equals that. But then, of course, when you pass the limit, you get 0. So that's less than 1. So according to the ratio test, we have absolute convergence. Well, here all the terms are positive anyway, so absolute versus regular convergence, same thing. So this series converges. As a matter of fact, it actually equals e squared, but I'm not going to tell you why that is. Stay tuned for a few videos from now, and we'll see why this is. But the ratio, so something like this, the ratio test shows convergence. Or here's another example, summation from 0 to infinity, n over 2 to the n. Again, a simple ratio test. So the n plus first term is this, with n replaced by n plus 1. And you divide by the nth term. That's the same as n plus 1 over n, and then 2 to the n over 2 to the n plus 1. All right, just multiply by this reciprocal. And then these powers cancel, leaving a 2 downstairs. And then, of course, in the limit, you've known for a long time that this limit goes to 1. So the limit goes to a half. So again, we get convergence because that's less than 1. So we have convergence by the ratio test. See, if you just had this series, that's a geometric series. That's a geometric series. This is like 1 plus a half plus a fourth, etc. And of course, you would know that converges. When you add the n here, it's no longer geometric series, but the ratio test works just as nicely. So there's a couple of examples of how you use the ratio test for convergence. In this section, they also talk about something called the root test. I'm not going to spend too much time on it because this doesn't come up as often as the ratio test. Basically, what you do is you examine, why is it called the root test? You examine the nth root of the nth term. Well, we take the absolute value of the nth term and take its nth root. And you ask whether that tends to a limit. Suppose it tends to a limit L. Then you get the same answers as for the ratio test. If L is less than 1, you get convergence, greater than 1, divergence, equals 1, no conclusion. All right, so the results, depending on whether L is less than 1, greater than 1, equal to 1, same results as the ratio test. So every so often, like especially when you have series where you have powers involved, like a lot of things raised to the nth power, then taking the nth root is particularly simple. Okay, but again, more often than not, you'll be using the ratio test. The main test we'll be using will be ratio, integral, and comparison, and of course geometric series. So that pretty much does it for all of our tests. This, I believe, is section 11, 5 or 6. Can't remember. I think it's 11.6. The next section basically ties everything together. It's like take a breath, and then they just throw a bunch of series at you and try to get you to understand how would you analyze it. What test would you use? If I just give a series, should you use the integral test? Should you use the comparison test, the ratio test? What should you do? So I'll put up some problems from this section and the next section, and then let you try to consolidate your knowledge about how you test for convergence of series. Then we'll go on